In this video, we're going to look at the average rate of change idea, but in this case, in the context of exponential functions. Okay, so the specific exponential function we're looking at in this problem is y of t is equal to e to the t. Okay, let's just do a couple examples here of making sure we understand what the data is showing us. So, typical average rate of change problem, we need to look at two particular rows of this function, okay? And therefore, these two rows would tell us that the average rate of change of the e to the t function on the interval t is equal to 1.1 to t is equal to 1.5 is the function evaluated at 1.5 minus the function evaluated at 1 divided by 1.5 minus 1. If you compute that out, you will use this number, and then dividing by this minus this. Use those four numbers and plug them into your calculator and compute the quotient of those two. You will get 3.52681. Okay. Computing using two other rows, maybe for example these two, okay, then the average rate of change, based on these numbers of the e to the t function on the interval t is equal to -2 to t is equal to -1.5 is going to turn out to be this number here, 0.17559. Okay, so what we can see here is that this number, the 0.17559, and the average rate of change on the other interval, 3.52681, that those are not equal to each other. 0.17559 is not equal to 3.52681. Okay. The conclusion is that we should probably compare what we are doing, compare the average rate of change of the exponential function e to the t to the function, for example, the linear function 2t minus 5. Okay. In that case, the 2t minus 5 example, we showed that the average rate of change from t is equal to a to t is equal to b was always equal to 2, no matter what you chose a and b to be. But here we're seeing that the average rate of change of the exponential function could be 1.7559, or it could be 3.52681. These numbers are not the same. Okay, so the average rate of change for a linear function is a constant, but the average rate of change for the exponential function is not a constant. Okay, so that's one difference between the exponential and the linear functions, is their average rates of change. Okay, there is something more interesting we can say about the average rate of change, as I will show you later on in this video. But first, let me point out in the context of a graph, what we just showed here. Probably shouldn't be too surprising. But what we are seeing here, remember the average rate of change idea is to compute the slope of the lines between these points, right? So what we are seeing here is that the average rate of change from -1 to -0.5 is this number, 0.289499. That's the slope of this line. So it's not very sloped, which is why it's a small number. And then from 0 to 0.5, the average rate of change comes out to be 1.29744. The slope of this line is a bit bigger because the line is a little bit more steeped. Okay. From 1 to 1.5, the average rate of change is 3.52681. And the average rate of change from 2 to 2.5 is 9.58688. So notice that these numbers, the average rates of change, are themselves getting bigger and bigger and bigger, which indicates that the slope of the lines are getting more and more steep. Okay, that's the implication, that the average rate of change is getting bigger and bigger. Okay, there is a pattern that's to be seen here. The pattern to be seen is that my claim, and we'll explore this as the video progresses, but my claim is that the average rate of change of the exponential function is not constant. But if you take the average rate of change and then divide by the exponential function, my claim is that this answer will be a constant. Okay? That's an interesting idea. And so let me show you an example of the computation that I mean here. So for example, let's take the interval 1 to 1.5, this one right here. So from 1 to 1.5. The average rate of change of e to the t on 1, t is equal to 1, 2, t is equal to 1.5. And then if I divide by the exponential function's value at t is equal to 1, I'll get the average rate of change is 3.52681, and then divide by the function value at that same time of 1. You'll get 2.71828. That should be some number. Okay? My claim is that if we do that same computation, maybe on another interval, the average rate of change of e to the t on t is equal to 2 to t is equal to 2.5, and then divide by the exponential function at t is equal to 2, that should come out to be 9.58688, and then divided by the function value there, which is 7.38906. My claim is that you should get a number, and that these two numbers should be the same. Okay? So let's go to a different setting where I can actually do some computations with my calculator. Our claim was that, let me find my mouse. The claim, okay, was that if we computed, say, for example, the average rate of change from 1.5 to 2, okay, look at the average rate of change, and it should simply be the 5.8143. If I divide that by this number, the function value at 1.5, I should get a number. So let's do that, 5.81473, and then divide by 4.48169, that I get a number which is 1.29744. Okay? If I were to choose two other points, the 2 to 2.5, the average rate of change between these two values, and therefore look at the average rate of change and then divide by the value of the exponential at that time. Okay, let's go ahead and do that. I will get 9.58688 and then divide by 7.38906. That I get the two values being the same, 1.29744 and 1.29744. This will happen, that you get a constant, if you choose any two of these values, okay, say 0.7, okay, I'll do this one more time just to see if it's more believable, 1.17559, and then divide that by 0.135335, and you also get 1.9745, the same constant, okay? So that was the number you get the same number, 1.29744 or something like that. Okay. So while the average rate of change is not a constant, it is true for exponential functions that the average rate of change of the exponential divided by the value of the exponential, that will be a constant. That is a true statement. Okay. In the next video, we'll explore the implications of this idea that the average rate of change divided by the function value is a constant for the exponential. We'll explore that idea.